Hello everybody and welcome to our presentation. My name is Diego Madariaga and I'm going to present our research work analyzing the adoption of QUIC from a mobile development perspective. This is a collaborative work with other team members of NIC Chile research labs at the University of Chile. The outline of this presentation is as follows. Firstly, I will give a brief introduction presenting the context and the motivation for this work. Secondly, I will present the network measurement methodology employed in this study. Next, we are going to talk about the data analysis and the results obtained. And finally, we will look at the conclusions of this research. First, I will give a brief overview of the current situation with regard to the analysis of QUIC traffic. After its introduction in 2013, QUIC protocol has received increasing attention in the community, and additionally, it has been adopted by the IETF for standardization since 2016. QUIC protocol has been an object of study for several pieces of research, and for example, it has been shown that QUIC outperforms HTTP2 over TCP in unstable wireless networks. In addition, some of these studies have focused on analyzing QUIC traffic from the overall network traffic, commonly using data from an internet service provider. These research studies estimated that between 2017 and 2018, QUIC accounted for 7 to 9% of total traffic volume. However, QUIC traffic volume is expected to be increased today, since at the time of these studies, almost all QUIC traffic was served by Google, with very few exceptions, such as the case of Snapchat. In contrast, now there are other important cases of technology companies adopting QUIC that were not part of these previous works. For example, Facebook and Uber Technologies started adopting QUIC for their services. Facebook started using its own implementation of IETF QUIC, and Uber started using an implementation of Google QUIC. Given the aforementioned, our research objective was to profile QUIC traffic from network measurements taken by mobile and user devices. This analysis becomes relevant for the following reasons. Differently from previous studies that analyzed QUIC traffic using data from an ISP, taking network measurements in user space allows us to clearly identify the mobile applications that are currently using QUIC, and therefore we can evidence newer efforts of companies to adopt this protocol. Additionally, as I mentioned before, previous experiments have shown that the performance of QUIC can be of particular interest for lossy wireless networks. Therefore, analyzing the traffic from mobile devices is relevant, as their internet traffic mostly goes through wireless networks using Wi-Fi or mobile data networks. Moreover, by 2022, 71% of total IP traffic is expected to be wireless. Thus, the importance of analyzing wireless traffic will also be increased. Now, I will discuss the methodology we used in order to obtain crowdsourced network measurements taken by mobile and user devices. We designed an Android framework capable of periodically taking network flow measurements through passive monitoring of active connections, in what we call a PEPA methodology. This methodology presents two fundamental properties: a periodic behavior and a passive behavior. We designed a periodic monitoring system to analyze network traffic from Android devices. The idea behind this periodicity is to obtain a good representation of the network traffic without having to be monitoring all the time, and without overloading the devices. This is achieved by monitoring the user's traffic for 1 minute every 15 minutes. Our passive monitoring system was designed to use Android's VPN service by implementing a local VPN server. Thus, the measurement system gains packet-level access without requiring root privileges. This local VPN server inserts itself in user space as man in the middle into existing connections on user devices. While our network measurement system is running, it extracts the following relevant information from each monitored network flow: the destination IP and destination port, the transport protocol used, that is TCP or UDP, start time and end time of the connection with microsecond precision, the number of transmitted and received bytes, the internet connection type, that is Wi-Fi or mobile, and the Android application that established the connection. From February to April this year, we distributed our Android network monitor to 160 real users. During that period, we collected data from 175,000 executions of our 1-minute measurement system. In total, we analyzed 1,850,000 internet traffic flows between TCP and UDP connections. These connections were established by 831 different Android applications to 35,000 different IP addresses. In order to gain further insights into the collected network flows, we performed a data processing on the measurements taken by our passive Android application. In particular, we wanted to identify network flows related to web traffic, that is, HTTP, HTTPS, and QUIC traffic. In order to identify HTTP and HTTPS traffic, we used Nmap tool to check the service running on each destination, IP and port, from our collected dataset. Thus, we can list the pair's IP address and port identified by Nmap as HTTP or HTTPS service. Regarding the network flows that seem to be using QUIC protocol, that is, UDP flows to a destination IP on port 443, we performed an analysis to check the availability of QUIC on these IP addresses. For that, we used two complementary methodologies. Firstly, we tried to connect to these IP addresses using HTTP over TCP connections. In case of success, we checked the alternative service header in their HTTP responses, where the service can advertise support for different QUIC versions. Secondly, we used the Lightspeed QUIC library to check the support for different QUIC versions on the IP addresses analyzed. Additionally, for each IP address running a web service using HTTP, HTTPS, or QUIC, we tried to establish a secure HTTP connection in order to analyze its SSL certificate and thus obtain the server's common name and organization. Using this methodology, the 82% of all IP addresses running a web service were successfully resolved to a common name and to an organization. In particular, all IP addresses running QUIC were included in this 82%. That is to say, there was no endpoint in our dataset that only supported QUIC and no TCP. This brings us to the next topic, which is related to the data analysis and the results obtained. When analyzing the overall network traffic generated by Android devices, including Wi-Fi and mobile data traffic, we found that 23% of the total traffic volume used QUIC. In addition, we found that the volume of QUIC traffic was different when analyzing Wi-Fi traffic and mobile data traffic. On the one hand, QUIC traffic accounted for more than 26% of Wi-Fi traffic, and on the other hand, QUIC traffic accounted for less than 11% of mobile data traffic. However, All these values are still higher than the volume of QUIC traffic previously estimated. As mentioned before, between 2017 and 2018, QUIC was estimated to account for up to 9% of total network traffic. After inspecting our database, we found 173 different Android applications using QUIC, out of a total of 831 apps analyzed. This represents an important increase in the number of Android applications adopting QUIC protocol, compared to what was stated in previous studies. Indeed, according to a previous work, by 2018, only 32 Android applications were found to use QUIC, out of a higher number of total apps analyzed. As stated by that research work, all these apps were developed by Google with the only exception of a Snapchat application. In our dataset, we found that only 20 of the 173 apps using QUIC were developed by Google. Accordingly, we can evidence a greater and meaningful diversity of developers in the remaining 153 non-Google applications that use QUIC. Looking in more detail at these 173 apps using QUIC, we found that, as expected, some of the Google apps presented a remarkably high volume of QUIC traffic, as the case of YouTube, Google Chrome, Google Photos, and Maps. Nevertheless, we also found evidence of other popular non-Google apps with high volume of QUIC traffic, as the case of Facebook, Instagram, Uber, and Snapchat. We also wanted to look into the organizations serving QUIC. According to our dataset, QUIC traffic in Android devices is mainly served by 4 major organizations: Google, Facebook, Snap Inc., and Uber Technologies. It is important to clarify that the volume of QUIC traffic served by Google is still significantly higher than for the rest of the organizations. In order to establish the degree to which these organizations have adopted QUIC into their mobile services, we analyzed the distribution of all the web traffic served by these 4 major organizations. As it can be seen, most of the web traffic served by Google, Snap, and Uber to Android devices used QUIC protocol. In contrast, a low portion of the traffic served by Facebook to Android applications used QUIC, accounting for only 3% of total web traffic volume served by this company. Now, we can also analyze QUIC traffic and look into the interaction between Android applications and the organizations serving QUIC content. Before doing that, we can first aggregate the applications that used QUIC in the following meaningful groups: applications developed by Google, applications developed or owned by Facebook, including Instagram and WhatsApp, applications developed by Uber, Snapchat application, and all remaining apps. We can then examine the distribution of QUIC traffic from these Android applications to QUIC servers belonging to different organizations. According to the dataset used in this study, all QUIC traffic generated by Uber's apps was served by their own servers. Similarly, almost all QUIC traffic generated by Facebook apps was served by Facebook itself, and almost all QUIC traffic generated by Google apps was delivered by Google. In contrast, the majority of QUIC traffic generated by Snapchat app was served by Google, whereas only a short portion was delivered by Snap servers. Finally, regarding the group of other apps, which aggregates the majority of apps using QUIC, almost all of their QUIC traffic was served by Google. At analyzing in detail this last group, 80% of all their QUIC connections were resolved to only 5 different common names. All these common names belong to Google, and they seem to be highly related to common embedded Google software development kits, such as Google Analytics or Google Mobile Ads. In conclusion, QUIC is growing very quickly, and it becomes relevant to keep track of its use. We presented a study on profiling the adoption of QUIC based on empirical crowdsourced traffic data measured in mobile devices. We collected valuable traffic information directly in user space, providing new insights with respect to previous related research studies. In particular, we looked into the Android applications using QUIC, the organization serving this content, and the flow of QUIC traffic among these actors. We reported a significantly larger number of Android applications using QUIC and evidenced an increasing QUIC adoption by major mobile applications and technology companies. The findings of this work take on great relevance as they are based on empirical traffic data measured in user space, which accurately represent the internet usage of mobile users in the wild. As future work, a temporal analysis could be performed to track the evolution of QUIC from a mobile development perspective during a longer period. I hope you have found this presentation useful. Thank you.